Hello everyone. Today I am going to talk about geometrical behavior of light and wavefront and vergence. And I would like to tell that this presentation or video is basically for optometry student, and I'm going to talk about this topic especially as an optometry student, especially first year, second year. So let's talk about the what is the difference between physical geometrical optics and the physical optics or wave optics. So basically geometrical optics and what do you say wave optics. So geometrical optics deals with the geometrical shapes, so that's why we deal with the refraction, reflection, and focal point, and all these things where we calculate with the help of shapes, especially triangle and angle, all these things. So this is basically geometrical optics. But in case of wave optics, it's more about advanced things and more about giving the answer about the basic nature of optics, which is basically diffraction, polarization, interference, and all these things. So as a student, we have to understand that geometrical optics deals with the uh, nature of optics, which basically the most important as a optometric point of view is the focal distances, reflection, refraction, which is going to help us in further dealing with ophthalmic dispensing, contact lenses, and all the machines and focal length and all telescopes, low vision devices, and all these things. But the real question where we deal with a lot of nature of optics, the answer we can found in the wave optics. So the current series of videos we will talk about geometrical optics and not the wave optics. Definitely wave optics will come later. And so in case of geometrical optics, the behavior of light, geometrical behavior of light, the main concept always lies in the concept of wavefront and the vergence. So today I'm going to talk about concept of wavefront. First wavefront, and then vergence and few calculations so that we understand from basics. So wavefront, we have to draw one thing about wavefront is this picture. When you see that this is the point source of light, and light goes like this in every direction from the point source. And imagine if there is a trough and crest of wave going from each point, and imagine that if the wave, if it is medium is same, all air and light from the point source, imagine in certain time at whatever certain time that light travels at the same speed and same medium, it travels equally, and at a point where phase is coherent, then the front of the light is called wavefront. Wavefront is sometimes imaginary, we say, sometimes real. It doesn't matter what it is. But the concept of wavefront is the distance at which the every light rays, that wave has same phase, and from the point source is same distance. And that imaginary point, the curvature, is called wavefront. Can you see? This is the curvature, isn't it? From this point, this is the curvature. From this point, this is the curvature. And many times in books, you see such a pictures. Let me show you. The round and round and round at the point source, and something like that. You see all the way. And all the textbook you see that, which means this point has same phase of the light from this point and this point and this point and this point and this point. For this circle wavefront, this point, this point, this point, and all these points have same phase, and it travels the same distance from the point where we consider medium is same, not necessarily one, but medium is same. So this is the concept of wavefront. Now the vergence in wavefront is definitely each other's back. So vergence is basically not a complex topic, but many of the students forgot. If you ask the student, they will answer like divergence and convergence. It's not that. The vergence is The way to quantify the curvature of wavefront. Now see, you have to understand wavefront. If you want to understand vergence is basically way to quantify the curvature of wavefront. See, this wavefront has more curved and compared to this wavefront, and this wavefront is more compared to this wavefront, and this wavefront is more curved if we draw more, and this is more curved if compared to this one. So the curvature of the wavefront, vergence is way to quantify the curvature of the wavefront. So it's basic simple thing. You can so all the textbook gives that concept of vergence, but not, yeah, we know that vergence is divergence and convergence, but it's not that. So another thing I want to emphasize is the real point source always give divergence light. In nature, it's not possible to have convergence light without a plus lens. So it's always important plus lens or plus mirror or whatever. But from the point source, it always emit divergent light. So you must understand that concept. So vergence, basically vergence is the way to quantify. Let's take an example. This is the point source and this is the wavefront. So here's another concept. The distance from here, let's take it R1, and this wavefront R2, this wavefront R3, and this wavefront is R4. We can easily tell that the curvature of R1 is greater than curvature of R2, then curvature of R3, and then curvature of R4. So by definition, vergence is way to quantify the curvature of wavefront. So more curvature is in R1. So we can tell R1 has more vergence, isn't it? Simple. So R4 is less vergence. So as we can see from the point source, as you move away, then the vergence decreases all the time. So this is the simple trick to understand. Simple thing. It's not a complicated thing to understand. So another way we can think, but we can also tell that R1 is more curved, but at the same time R1 has less distance. From the distance point of view, R4 is greater, R3 is less greater, R2 is less greater, and R1 is less greater. So, from this point of view, we can understand vergence is inverse of the distance, isn't it? It's simple. The way to quantify, as you move away from the point source, the curvature decreases. That's why vergence decreases. So, vergence is inverse to the inverse from the distance. So you can see easily in all the case you see something like that, uh, n divided by q. The q is distance, n is refractive index, and you see all time this type of question. For example, this is the point source and light emits from here. This is 10 centimeter. What is the vergence? So it's simple. If we take index is 1, if it is air, then 10 divided by 100 to make centimeters. So minus 10 diopter. Why minus? Because it's diverging, isn't it? Simple. So if you want to calculate from this distance 20 centimeter, then it's simple. 1 divided by 20 divided by 100. Why I'm dividing by 100? Because it's I want to do in meters. Definitely we know that. So 100 divided by minus 20 is equal to minus 5 diopter. So as you move from the point source away, then you know that vergence decreases. It's simple as that. So let's take another example, and this time I want to make it a little bit trickier. Because see, I want to put this plus lens here, and from plus lens, light converges, focuses here, and again diverges. It's always happen like that, isn't it? Light come when it comes to the focal point, it will diverge. So in this case, this is tricky case. In this case, this is the point B, for example, and this is the point A, and this is the point C. If we want to calculate vergence at the point of A and vergence at the point of C, then we have to consider distance not from the source, but from the focal point. Essentially important. And in this case, let's take an example from B to A, the distance is 10 centimeter. And if we want to calculate, it's simple, 1 divided by 10 divided by 100, which is 10 diopter. But in case of this, it's 10 diopter plus, because this ray is converging, not diverging. But in case of this, let's take an example from B to C, is again 10 centimeter. But in case of this case, uh, vergence is 1 divided by 10 divided by 100. Vergence is 10 diopter, but in case of this, vergence is negative because it's divergence. We always know that converging light is plus in diopter, which is converging, in minus, which is diverging. So it's not always that we take distance from the point source. We have to take distance from focal point too. But it's always the same case. Why is always the same case? Let me clear. If you take it as a point source and then you take it here, let's say divergent light. So you want to know the vergence at the point source. So what happened there? If vergence at the point port, one index and the distance is 0, it's always infinity. This is the point source. It's infinity. But let's take an example. This is the focal point. So here you want to calculate the vergence, which is again the distance is 0, which is again infinity. So at the point source, at the focal point, vergence is always infinity. So we have to understand this concept in a long term, because when you are going to talk about the telescope, when you are going to talk about the refractive error correction, when you are going to talk about contact lenses, and in case of dispensing, in case of orthotics, there are a lot of places we have to understand this concept. So change in vergence, how it happens. So let's take an example how versions interact with each other. It's always simple. Versions always interact with each other with you add the versions, isn't it? Let's take an example. If there is a point source and it gives divergent light, and you put one plus lens here. So let's take an example of plus lens plus 10 diopter. And let's take an example. This is the distance of 10 centimeter. We know from previously the vergence at this point, remember, not at this point, not at this point, not at this point, but at exactly the point where it interacts with the lens. Then vergence is simply 1 divided by 10 centimeter or divided by 100, which is meter. Here is minus because it's divergent. So 10 diopter divergence, and then the light vergence here exactly at interacting point between the lens and the point source is minus 10 diopter, and the power of a lens is plus 10 diopter. Then the light coming out from the lens is parallel, because minus 10 diopter plus 10 diopter is 0. 0 means light has parallel light. Wavefront are parallel. Rays are parallel. So wavefront has a curvature of infinity. Okay, you have later on we will discuss about that. So you have to understand how it interacts with the lens. So let's take an example of it always lies something like that. Let's take an example of cornea. Front surface of cornea and the back surface of cornea. Front surface of cornea is, let's take an example, 48. Back surface of cornea, let's take example 6. Then why we call what is the power of the cornea in total? Plus 48 minus 6 is equal to almost 42, almost 42 and 43, whatever, it doesn't matter. So this this is how we calculate. It's simply adding the power, but it's not simple as that, because as we progress from the one surface to multiple surface, from thin lenses from to thick lenses. So I want to tell you one thing which is very important, and we'll talk about in single surface refractive interference, but I just wanted to cover here. Whenever power, in case of diopter, it comes, there is three things you have to understand. One is surface curvature, that is R1, R2, and whatever. Second most important is refractive index, Third, and less important but important because of thick lens and all these things, is the distance, thickness, or distance, separation, that matters. These three things are always the key component when it comes to the power, when it comes to the power of a surface, or when it comes to the power of an optical system. So you have to understand these concepts before jumping up to anything. So let me conclude for you for today. Whenever you have to understand the concept of wavefront. See, this is very important. Second, vergence. Vergence is the way to quantify the curvature of wavefront. Please understand what is wavefront and how it goes. And another thing, when you are calculating vergence, you have to understand vergence is reciprocal of distance, or vergence is directly proportional to the curvature of wavefront. The wavefront is more curved, vergence is more high. And whenever it comes to convergence, there is two things: divergence or convergence. There is no convergence naturally. In case of nature, directly there is nothing like convergence. It has to go from some plus lens. So in nature you will see always divergent light, or if it crosses a lot of distance, then it's parallel. Because see, if it is a point source, this is more curved, and as distance travel, the curvature reduces, and if it distance largely cross, then the wavefront becomes parallel. That's why we call, when light comes from sun, it's directly parallel, and there is no curvature. In case of optometry, we always take 6 meters as infinity. Definitely 6 meters is not infinity, but let's take example. What happens if we do this convergence at 6 meters? It's way lesser, isn't it? So that's why we take it as an optical infinity, 6 meters. So if you travel a lot of distance, here's the if it is point source, here the vergence is so high. But as you cross distance, then vergence becomes less, curvature become less curved, but the r going to increase from r5 to r1. R5 is way higher, the r1 is a distance. So you have to understand this concept. Another concept, you have to understand how vergence interacts with each other. One surface vergence to another surface when it travels from the distance. And one more thing, you have to understand, I take all the example from 1 divided by whatever distance. It's not like that. It's always in above there is a refractive index and divide by distance. I take an example from air, that's why I take n. It's equal to 1, but it's not that. When we're going to talk about our real eye, so it's way complicated, because outside of the eye it's 1, inside of the eye we it's always approximately 1.3, 1.4, or whatever. So eyeball has very different optics, because outside of the eyeball it's 1, but inside of the eyeball it depends on the cornea, it depends on aqueous humor, lens, or cortex and nucleus. So all the things happen there. So you have to understand these concepts. So you have to understand these concepts and work slowly. Okay, so I'll see you in the next video with the single surface refractive interference. Till then, thank you so much. uh, Bye bye.